Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. First, before we proceed, I'd like to request our members to kindly subscribe to our channel and also engage us in the comment section, and also check also some links which I normally put in our description boxes of various videos which are going to be similar to these particular topics under discussion. So in today's discussion, we're going to look at one of the principles of quantum mechanics. And this, of course, is going to lay a basis for us in understanding the wave-particle duality of matter. Now, in this case, we're going to see that basically, aside differentiated from some of our videos, the concept of quantum mechanics differs from classical mechanics in a sense that quantum mechanics is going to deal with basically of the nature of particles at a microscopic level. And we're going to see that these are basically a range of particles which are of nature of the subatomic particles, whereas in classical mechanics, we're going to see that this is going to deal with the aspect of particles in macroscopic level. So there's a difference between these two specific fields of perhaps physical science, whereby we're going to see that they're going to be dealing with this particular aspect or scope of nature using this specific of course, category of particles. Now, in a sense, the principles of quantum mechanics are going to assist us understand the concept of or the characteristics of various particles at the microscopic level. And today we're going to look at the concept of waves and particles. And this is going to give us a basis, as I said, for understanding the concept of a wave-particle duality, which forms a basis for various discussions in, under the topic of quantum mechanics. Now, for us to understand this particular concept of wave-particle duality, it will be essential for us to understand the characteristics of this particular aspect of waves and particles in their distinct way, in a sense that the merger of the two then are going to give us a basis for trying to find a baseline for discussion under the concept of the broader concept of quantum mechanics. Now, in this case, I'm going to look at the characteristics of waves and particles, as I've said, and then, of course, I'm going to look at a few of experimental evidence which have been done in order to confirm this specific aspect of the wave-particle duality. Now, if you try to look at the concept of waves from a previous definition, we define a wave as an aspect that is spreading out, or a disturbance that is spreading out in a media uniformly in all directions. And I can give an example of a visual, or rather an illustrative example of what we can refer to as a wave. In this case, of course, it's going to be emanating from this specific point and spreading out uniformly in all directions. So this is some kind of a disturbance, as I've said, which is going to be propagated through a media in all directions. Now, for the case of a particle, then a particle is, of course, has got mass and weight. And of course, in this case, we can be able to see this specific particle. Now, in a sense, then therefore, we can differentiate between waves and particles in that waves are physical and, of course, I mean, particles are physical and waves cannot be seen, and or they cannot be confined to a particular region in space in contrast to a particle. Now, in this case, if we look at this specific case, if this is a particle, then if a force is applied on this particle, it's going to move in that particular direction. And of course, it's going to undergo a displacement to another position, perhaps from P to P prime, given as such. So this is one of the characteristics of particles, that we can be able to influence their particular position by using the concept of a force from the initial position to, of course, a particular position that we want. But this specific characteristic is not going to be achievable insofar as waves are concerned, since these physical characteristics of waves are not present, as I've mentioned, for the case of particles. Now, in this case, I'm going to look at various characteristics of the two, and then, of course, from the experimental evidence that I've mentioned, that I'm going to give at the end of our discussion, it's going to shed light for us how we can find perhaps a common point between waves and particles. Now, in this case, I'm going to start with these specific disturbances that I've referred to as waves, which are spreading uniformly in all directions. So in this case, waves can be characterized using various aspects, and one of them that we're going to look at is what we refer to as wavelength. Now, this wavelength refers to the displacement of a particular wave from a point to another one. And in our discussion on the concept of anatomy of a wave, of course, I've given a representation of a sine wave or a wave that's a longitudinal wave on Cartesian coordinates, and I'll be given an example of this specific illustration. Now, in this case, this of course is a transverse wave, and I'll be given it an example of this specific illustration from a Cartesian coordinate system. Now, in this case, this is going to be a description of a wave that is moving along this x-axis under this particular Cartesian coordinate system. And of course, we said that if this is a point of origin or an equilibrium position, then therefore we're going to have a displacement from this equilibrium position to this highest point, perhaps along the y-axis. And this is going to be given in terms of A. And of course, I'm going to give what this basically this A represents. And then we are going to have another one from this highest point to another highest point, and we're going to give this one in terms of lambda. This basically is a displacement from a single position to another one. And this wave is going to go in forms of cycles. And then, of course, we said that this wave is going to be undergoing displacement with the time. And in this case, I'm going to give a displacement in terms of r, and perhaps time in terms of t. So this is going to be a function of course, a displacement with time given as such. And later on, we're going to describe some of the physical characteristics of this particular wave, how we can describe them. Now, in essence, I've mentioned the concept of a wavelength. Therefore, the wavelength is going to be the distance between what we can refer to as one crest to another, or one trough to another, that is going to describe this specific aspect of a wave. The next, we can characterize a wave using what we refer to as frequency. And frequency, this is the number of cycles which are going to be realized by this wave per second. So therefore, this is going to be given as the number of displacement per second. And of course, it's going to be given using this specific symbol that I've given on the board. And then we're going to see that I've mentioned the concept of this specific A. And therefore, this A refers to what we call the amplitude. And this is the maximum displacement from the equilibrium position given in terms of A given as such. And then we're going to have what we refer to as the fourth characteristic of a wave is what we refer to as the wave velocity. Now, the wave velocity is going to be given in terms of omega. Now, we're going to see that as this particular wave travels, it's going to return to its initial position in this specific sense, but there will be an element of time which has been consumed from this initial position to the last one. And therefore, we can characterize this particular wave as it travels in terms of displacement with respect to time. And that is, since it goes in form of cycles, this is going to be in terms of this particular velocity that we refer to as omega. And later on, we're going to look at the aspect of angular displacement that is going to be described, of course, in terms with respect to time, that is going to be described in terms of omega. And then we're going to look at another aspect. A wave can be characterized using what we refer to as a phase, which is basically the displacement. I can give another wave that is going to be characterized using this particular, of course, wave. And then the displacement from this specific point along the x-axis to this one can be given in terms of a wave, a phase. And this is one of the characteristics of a wave, as we're going to see, especially under the concept of a transformation of trigonometric functions. And of course, that one is going to be given in terms of a phase. And then lastly, we're going to look at another characteristic of a wave that we can refer to as intensity. And of course, this is going to be started later in another discussion, but I'm going to leave it an initial given as I given as such. So these are some of the characteristics of waves that we're going to encounter, which of course are going to appear in these specific concepts under various discussions on the concept of quantum mechanics. Now that we have said this particular concept of waves and particles are going to be having specific characteristics which are going to be similar, and that of course is going to be explained under the dual dual nature or the dual nature of matter as I've mentioned. Now, in this case, for particles, we can as well look at the few characteristics that we're going to, of course, encounter. And of course, these are going to be in terms of what we refer to as mass. So particles possess mass, which is going to be given in terms of air. And then we're going to see that particles can be described in terms of velocity, which is their displacement, as I've given an example. That is displacement with respect to time, of course, is going to describe the aspect of velocity of particles. And then we can describe another aspect that we refer to as momentum. Momentum is the product of velocity and, of course, this particular aspect of mass. So therefore, the mass and velocity is going to give us what we refer to as momentum, given an initial as p. And later we're going to see that this is the product of the two that I've listed above. And then we're going to characterize particles using what we refer to as energy. And of course, this is the energy which is going to appear in various forms, as we are going to see. But we can give the overall energy of a particle as a summation of kinetic energy plus the potential energy given as such. So we're also going to have a vivid description of this specific aspect of particles given as such. So we're going to have a close look at these two specific characteristics of the two for particles and waves. We're going to see that there's going to be an interplay that is going to result in the overall aspect of the dual nature of matter, and that's going to form a basis for some of the principles of our quantum mechanics which I've listed above. So I'd like to request our members to kindly be noting about this specific characteristic, since they are going to be holding a particular significance, especially on these specific initials that we are using. They are going to appear in one way or another in some of our discussions. And kindly note that, of course, as we are going to use them, they are going to imply the various names that I've given them, preceding them, just as I've written them on the board. So that is it for now, guys. Check our description boxes for various links of other videos, and kindly subscribe to our channel so that you can be getting more updates. So that is it for now, guys. Bye, God bless you. Catch us in our next video.